Welcome. Here, we break down complex electrical engineering concepts into simple, practical, and engaging explanations. So stay connected with the world of electrical engineering.
The Wenner method, also known as the Wenner Four-Electrode Method or Wenner Four-Point Method, is one of the most widely used techniques for measuring soil resistivity. Developed by Dr. Frank Wenner of the US National Bureau of Standards in 1915, this method has become the standard approach for geotechnical investigations and grounding system design. Now we come to the fundamental principle of this method. The Wenner method operates on the principle of injecting a known current into the soil through two outer electrodes and measuring the resulting potential difference between two inner electrodes. This arrangement allows for accurate determination of the soil's electrical resistivity. The Wenner method employs four electrodes arranged in a straight line with equal spacing between consecutive electrodes. The configuration is as follows. C1 is the first outer electrode connected to the positive terminal of the current source. P1 is the potential electrode. This is the first inner electrode used for voltage measurement. P2 is another potential electrode. This is the second inner electrode used for voltage measurement. C2 is the current electrode. This is the second outer electrode connected to the negative terminal of the current source. This is the resistance measuring unit. The current source and voltage measuring units are integrated in this instrument. The spacing between each consecutive electrode is denoted as A, making the total spread of the electrode array equal to 3A. The four electrodes are driven into the ground to a depth typically of 10 to 15 centimeters. This shallow penetration ensures that the depth of electrode insertion does not significantly affect the measurement. The electrodes should be vertically aligned and positioned in a straight line with precise equal spacing. A known alternating current of low frequency, AC or even DC, is passed between the two outer electrodes, C1 and C2. The use of AC helps to minimize polarization effects at the electrode-soil interface. Modern instruments such as the Megger earth resistance tester automatically generate the appropriate current. The potential difference between the two inner electrodes, P1 and P2, is measured by the instrument. The instrument automatically calculates the resistance R using Ohm's law. This means the instrument shows the ratio of measured voltage to the injected current. The apparent resistivity, RHA, of the soil is calculated using the formula RHO equals 2pi into I into R. RO equals apparent resistivity in ohm meters. Pi equals approximately 3.14159. A equals electrode spacing in meters. R equals measured resistance in ohms. To understand the soil stratification and resistivity variation with depth, measurements are taken at multiple electrode spacings. In our test, 5 different spacings were used: 1 meter, 2 meters, 5 meters, 10 meters, and 15 meters. The Wenner method probes the soil to an approximate depth equal to the electrode spacing A. More precisely, the effective depth of measurement is approximately 0.7 to 1.0 times the electrode spacing. Therefore, 1 meter spacing investigates approximately 0.7 to 1.0 meters. Depth 2 meter spacing investigates approximately 1.4 to 2.0 meters. Depth 5 meter spacing investigates approximately 3.5 to 5.0 meters depth. 10 meter spacing investigates approximately 7.0 to 10.0 meters. Depth 15 meter spacing investigates approximately 10.5 to 15.0 meters depth. As the electrode spacing increases, deeper soil layers contribute more significantly to the measured apparent resistivity. To account for soil anisotropy, the variation of soil properties with direction, measurements are typically conducted along multiple directions from a central point. In our test, 8 directions were investigated. Cardinal directions: north, east, south, west. Intercardinal directions: northeast, southeast, southwest, northwest. This comprehensive directional survey reveals variations in soil composition across different directions. Now we go to a practical example for better understanding. This document presents the results of Electrical Resistivity Test conducted to determine soil resistivity at various depths and directions. Resistivity measurements were taken at 5 probe spacing depths: 1 meter, 2 meters, 5 meters, 10 meters, and 15 meters across 8 directional profiles: north, northeast, east, southeast, south, southwest, west, and northwest. North direction 1. Mega readings ranged from 5.20 ohms at 1 meter spacing to 0.22 ohms at 15 meter spacing, with corresponding apparent resistivities of 32.69, 13.84, 41.17, 40.86, and 20.74 ohm meters respectively. The sum of apparent resistivity is 169.40 ohm meters, yielding an average apparent resistivity of 33.88 ohm meters. Northeast direction 2. Measurements showed mega readings from 4.97 to 0.19 ohms, with apparent resistivities ranging from 31.24 to 17.91 ohm meters. The average apparent resistivity is 29.45 ohm meters. East direction 3. Readings varied from 4.92 to 0.21 ohms, producing apparent resistivities between 30.93 and 19.80 ohm meters. The average apparent resistivity is 30.10 ohm meters. Southeast direction 4. This direction showed the lowest overall resistivity, with mega readings from 3.89 to 0.17 ohms and apparent resistivities from 24.45 to 16.03 ohm meters. The average apparent resistivity is 22.16 ohm meters. South direction 5. Measurements ranged from 4.81 to 0.18 ohms, with apparent resistivities from 30.23 to 16.97 ohm meters. The average apparent resistivity is 28.52 ohm meters. Southwest direction 6. Readings showed 4.21 to 0.18 ohms, with apparent resistivities from 26.48 to 16.97 ohm meters. The average apparent resistivity is 25.28 ohm meters. West direction 7. This direction exhibited relatively low resistivity, with readings from 3.89 to 0.15 ohms and apparent resistivities from 24.45 to 14.14 ohm meters. The average apparent resistivity is 21.99 ohm meters. Northwest direction 8. Measurements ranged from 4.10 to 0.15 ohms, with apparent resistivities from 25.77 to 14.14 ohm meters. The average apparent resistivity is 22.20 ohm meters. The highest resistivity was observed in the north direction at 33.88 ohm meters, while the lowest was in the west direction at 21.99 ohm meters. The resistivity values show significant directional variation, indicating soil anisotropy at this location. Now we shall draw a polar curve. The 8 directions were carefully chosen to provide comprehensive coverage around the test location. Starting from the top and moving clockwise, we have north at the top, northeast at 45 degrees, east to the right, southeast at 135 degrees, south at the bottom, southwest at 225 degrees, west to the left, and northwest at 315 degrees. Now, let's examine the actual measurements. Each blue dot on the graph represents the average apparent resistivity measured in that particular direction. The distance of each point from the center corresponds to its resistivity value. North direction shows the highest resistivity at 33.88 ohm meters. Notice how far this point extends from the center. Moving to northeast, we see 29.45 ohm meters, slightly lower than north. East measures 30.10 ohm meters, maintaining relatively high resistivity. Southeast drops significantly to 22.16 ohm meters. South rises again to 28.52 ohm meters. Southwest shows 25.28 ohm meters. West records 21.99 ohm meters, our absolute minimum. And finally, northwest measures 22.20 ohm meters, nearly identical to west. When we connect all these measurement points, we create what's called a polar curve or polar plot. Notice that this is not a perfect circle. It's an irregular shape. We now construct a circle, shown here in red, with a dashed outline that has exactly the same area as our polar curve. This is called the equivalent circle. Why a circle? Because a circle represents perfectly isotropic conditions, the same resistivity in all directions. In practical grounding system design, we need a single resistivity value, not 8 different values for 8 different directions. The equivalent circle provides us with that single representative value while still honoring all the directional measurements we took. The radius of this equivalent circle is the key to our final result. You can see the radius drawn here as a red line with an arrow. The length of the radius in the same scale is 25.33. Hence, the equivalent soil resistivity at this location is 25.33 ohm meters. This single value encapsulates all 8 directional measurements and all 5 depth measurements from our comprehensive field testing program.
Thanks for watching. We hope this video helped you understand electrical engineering concepts better. If you enjoyed the content, don't forget to like, share, and leave your thoughts in the comments. Stay with us and stay updated with more videos on transmission lines, substations, and power systems. Until next time, stay curious, keep learning, and keep the power flowing.